what we want to do is a simple example of diagonalization. Okay, and as you're going to see, it takes some work, but what I want to do now is not just follow kind of a recipe, which is what we're going to do in the next examples. I want to, from this example, extract the ideas of the recipe. Okay, so to understand what's going on and how we diagonalize in general. Okay, so here's the example. Let's look at the matrix A equals 1, 2, 3, 2. Do you agree that if something deserves to be called a simple example, this is probably it? Okay, so here's a matrix. A corresponds to a linear map. Okay, so define, let T of V be equal to A V. So now we have a linear map given by the matrix A. Let's write things more explicitly, i.e., so the map T is going to go from where to where? What are the domain and range spaces?
2 by 2 matrix.
No. V, help. Simple example. V to V, what is V?
R4.
Not R4, it's a 2 by 2 matrix. R2, right? T, what T does, T of x, y equals A, x, y, right? That's which is 1, 2, 3, 2, x, y, right? T is a map from R2 to R2. Good? Gotcha. Everybody good? Okay. And we can even write this explicitly and then forget that it stemmed from a matrix. Okay, but we don't want to forget that. A is going to play an important role. So what is this? This is x plus 2y and 3x plus 2y. That's what T does to xy. T goes from R2 to R2. Good, everybody? Sure? Nobody confused? Say yes. Okay. Okay, so now let's recall what we're doing. We're seeking a vector xy, a non-zero vector xy, such that xy, a vector xy and the scalar alpha, such that T of V equals alpha V. Such that T of V equals alpha V. I.e., not I.e. I.e. is for example, right? No, that's E.g. I.e. is good. Sorry. I.e., what do I want? I want 1, 2, 3, 2 times x, y to be equal to alpha times x, y. Do you agree? That's what I'm looking for. An x, a y, and an alpha that satisfy this. Good? Then this xy would be, using the terminology we defined, an eigenvector, and this alpha would be an eigenvalue corresponding to this a or to this t. Doesn't matter. We're thinking of them as the same thing. Good? Okay. So I'm just going to rephrase several times what we're saying in order to see how we get it. Okay? So we're looking for an xy and alpha such that a times v minus alpha times v equals 0. That's a different way of saying the same thing. Do you agree? Okay. Another way of saying the same thing is that 1, 2, 3, 2 I want to somehow do a distributive sort of thing on the left-hand side. I want to say it's something times xy. So what is that something going to be? Here I'm multiplying by a matrix, here I'm multiplying by a scalar. So how do I translate the scalar to become a matrix? Exactly, exactly. It's the identity with alphas on the diagonal. So I can write it 1, 2, 3, 2 minus alpha I. So these are parentheses. This is not a matrix. Times xy equals 0, 0. Do you agree that this is the same thing? Everybody good? Sure? Maybe we'll write it over here. So alpha times xy is the same as alpha 0, 0 times xy. Right? This is alpha x, alpha y, and here it's alpha x plus 0y, 0x plus alpha y. Do you agree that these are the same thing? Okay. So I want to break this into 2 steps, and you'll see why in a second. So let's throw this into here. So here I'm going to write alpha 0, 0 alpha. Good? This is the same thing, right? And now I'm going to say, okay, this is the matrix. Here we have the matrix. This is the matrix. This is the matrix A minus alpha I. Do you agree? So now let's say in different words what we're doing. We're looking for a vector xy that solves this. That would be an eigenvector. Okay? That translates into a solution to this. But now the same thing is written as a homogeneous system. Do you see that? Here's a matrix. I'm looking for solutions to the homogeneous system written here. Okay, I can take another step and even write it as 1 minus alpha, 2, 3, 2 minus alpha. That's this matrix times xy equals 0. Do you agree? This and this and this is the same thing. Okay? Good? So what we're looking for, I'm going to say it in different words. An eigenvector, a vector xy that solves this, or that solves this, is a vector which satisfies that A minus alpha I sends it to 0. Okay? So an eigenvector, from here I can see that in a vector xy, solving this system is a vector in the kernel of A minus alpha I. And remember, we can use the word kernel for a matrix. It makes perfect sense. It's the vectors that this matrix, not A. It's not the kernel of A. It's not the kernel of A itself. It's the kernel of A minus alpha I. Good? So a vector solving this is a vector in the kernel. Okay? Eigenvectors are elements in this kernel. In order to find eigenvectors, we have to find what is this kernel. Okay? Good? That's going to be one part of the theorem that we're going to have up in the next clip when we generalize this to a theorem. Good? So an eigenvector is an element in the kernel of A minus alpha I, or T minus alpha I, if you want to think of the map. And it leads up to this homogeneous system of equations, which is very simple here. right? This, I just want to squish these a bit so it's clear that this is a matrix. And we want to find solutions to this homogeneous system. Everybody with me? Okay, now let's say a few things. This is a homogeneous system, a 2 by 2 homogeneous system. And we had many characterizations of when does a system have a solution, when it has a unique solution, when it has infinitely many solutions, and so on. It's a homogeneous system. It always has a solution. Which solution does it always have? 0. We could always put 0, 0 here, and we're good. But we're not interested in finding 0, 0, right? Because we're looking for eigenvectors, and 0, 0 is not an eigenvector by definition, right? We want to form a basis of these guys, right? So we're not interested in the trivial solution. So we're asking, when does it have more than one solution? Non-trivial solutions. Good? Now, for a homogeneous system, in general, for a system of equations, it could have no solutions, which is not the case for a homogeneous one. It could have a unique solution, which could happen for a homogeneous one, or it could have infinitely many solutions. That's all the possibilities. For a homogeneous one, it either has only the trivial one, or it has infinitely many ones. Okay? So we're asking, when does this system have infinitely many solutions? If it does, there are going to be eigenvectors. If it doesn't, okay? So we're asking, when does this have infinitely many solutions? So let's write that as well. We want to know when this system, this homogeneous system, has infinitely many solutions, and not just the trivial one. Good? Let's call this matrix, at least temporarily, let's denote this matrix, well, A is taken, and B stands for our basis. Z is not a name for a matrix. Let's call it M for a matrix. Let's call it M for a second. Okay? So we know in general, I'm just recalling some facts that we know and discussed some time ago and kept reminding of them, but here I'm kind of collecting some stuff. So in general, there is a unique solution if and only if the rank is full. And what does full mean in this case? 2. Right? This is a 2 by 2 matrix. Full rank means 2. Okay? So there is a unique solution if and only if the rank is 2. Another if and only if for this would be that M is invertible. Right? And another if and only if is that the determinant of M is not 0. Do you agree? This is stuff we've discussed previously. Okay? So we're interested in the situation where there are infinitely many solutions, which is the complement of this for a homogeneous system. It's either this or infinitely many. So in our case, there are infinitely many solutions if and only if, let's write so, there are infinitely many solutions if and only if,
It's less than 2.
that's one way of saying it, but I want to pick this one up.
Determinant is 0.
The determinant is 0. Do you agree? Okay. So what we want to know is what is the determinant of that M. And remember that M was the matrix A minus alpha I. Okay. So let's continue and write that. So the conclusion is we are seeking alphas such that the determinant of m, which was the determinant of a minus alpha I, or in our example, the determinant of 1 minus alpha, 2, 3, 2 minus alpha, is 0. That's what we want to find. If we can find an alpha such that this determinant is 0, then for that alpha, there are going to be infinitely many solutions to the system. In particular, there are going to be non-trivial solutions to the system, and those solutions are precisely the xy's we're looking for, the eigenvectors. Good? Okay. Everybody still with me? Is the story clear? Okay. So let's go back a second and look at it again. We started from a matrix A. Okay? We started from a matrix A. An eigenvector is a vector that satisfies this. Right? We translated this to this system, right? To this system, where this is the matrix A minus alpha I. And now an eigenvector is a solution to this system, or an element in this kernel, right? It's going to have a non-zero solution if the determinant of this matrix is 0. Good? Okay. So we're here. We want to know, when is the determinant of this matrix 0? What's the determinant of this matrix? It's
1 minus 2.
right. The determinant of this matrix, right? We want to find 1 minus alpha times 2 minus alpha minus 6 equals 0. We want to solve this. We want to find alphas that solve this. What is this thing? What's written on this left-hand side? This is no longer a matrix. Right. This is a polynomial in the variable alpha. And we're looking for alphas that solve polynomial equals 0. What are such alphas called? Solutions or roots. We're looking for roots of this polynomial. Okay, let's understand what this polynomial is. So what do we have here? We have 2, right? 2 minus 6, so we're going to have here minus 4. And here we have minus alpha times minus alpha, that's an alpha squared. And we have here minus 2 alpha minus alpha. So minus 3 alpha equals 0. That's the polynomial. Okay? So we're looking for roots of this polynomial. Okay? Roots of this polynomial are going to be such alphas, are going to be eigenvalues. Okay? So roots of this polynomial are eigenvalues, are alphas that we're looking for. Do you agree? And this polynomial is called, it has a name, it's called the characteristic polynomial of A. Okay, the characteristic polynomial of A. So alpha squared minus 3 alpha minus 4, that's what we found in this example, is called the characteristic polynomial of A. Or of T, doesn't matter. Okay. Roots. Its roots are eigenvalues of eigenvalues and eigenvectors are going to have the same abbreviation, right? Ouch. Hmm? Yeah, maybe it's not a good idea to make them up. I'll look it up. Eigenvalues of A. So the eigenvalues are roots of the characteristic polynomial, which is the determinant of A minus alpha I. Okay, good? That's going to be the theorem. Okay, we're building the theorem from scratch. We're really inventing the theorem. Okay. So let's rewrite this polynomial. How do we find roots? The simplest way is, okay, you can use the formula or you can factor it, right? So let's call it P of alpha. Okay, so P of alpha, if you factor it, it's what? It's going to be alpha times something and alpha times something. So it's alpha squared minus 3 alpha. That's the product, so it's going to be a minus 1 and a minus 3, and we got to get a minus 4, so one of them has to be negative, minus 3.
Minus 4 and 1.
Minus 4 and 1, right, a minus. Yeah, so this is going to be plus, right? So alpha squared plus alpha minus 4, alpha minus 4, good. Okay, so what are the roots? Alpha 1, one of the roots, is negative 1. And alpha 2, which is 4, these are the eigenvalues. Good? And that's it. There are only 2 of them in this case. Good? Okay. So, these are the eigenvalues. They are the roots. These are the eigenvalues of A, which are the roots of, I'm saying things again and again and again, but we're building this, the roots of the polynomial, the characteristic polynomial, which is the determinant of A minus alpha I. Good? So, when I'm going to write the theorem, I'm going to say the eigenvalues of A or of T are the roots of the characteristic polynomial defined by A minus alpha I, determinant. And you're going to look at this and say, hey, well, this is not a polynomial. This is the determinant of a matrix. But when you have alpha as a variable here, this is a polynomial in the variable alpha. Okay? So when you see this, you're looking at a polynomial. Right? Let's look again at the previous board. This is a polynomial. It's this polynomial in alpha. Good? Everybody? Okay. So good. We found the eigenvalues. Now what do we need to find? The eigenvectors. So far we found the alphas for which this is going to be 0. Therefore, for which, again, I'm looking at the previous board. The previous board. So I've found the values for which the determinant of this matrix is 0, which is the same as saying this system has infinitely many solutions, and in particular, non-trivial ones. Okay? So now we want to find the solutions themselves. And the solutions themselves are the non-zero elements in this kernel. Okay? So step 1, find the alphas. Step 2, find the v's. Good? Okay, so let's write that as well. So we need to take each of these guys separately, plug them into that system, and solve it. Okay? So we need to find, so these are the eigenvalues. To find the corresponding eigenvectors, we plug in alpha 1 and alpha 2 into the system given by the kernel of A minus alpha I. Right? That's what we want to do. So let's do that. Remember that alpha 1 was negative 1 and alpha 2 was 4. Let's start with alpha 1, which was negative 1. I just want to write alpha 1 over here, to plug it into here. Okay? Look at this board, please. Ah, there you are. I'm going to plug it into here. So I'm going to erase this, erase everything, just leave the system, and let's do it. So the first time you see the process of diagonalization, it really looks like, oh boy, right? It's a bit, whoa. But in fact, we're just doing, each step is the needed step in order to do what we want to do, right? It's really leading itself, okay? And then it's going to be a theorem. So for alpha 1, which was negative 1, let's see what we get. I'm going to plug it here. Okay. So I'm going to get the system 1 minus negative 1, 1 minus negative 1, 2, 2, 3, 2 minus negative 1, 3, xy equals 0. That's the system I want to solve. Once I plugged in a concrete alpha, it's a concrete system. Okay, and we know how to solve this system. This is a system of two equations, two unknowns. In fact, they're the same equation written twice, right? So the solutions are 2x plus 2y equals 0, or 2x equals negative 2y, or x equals negative y. These are all the solutions. Do you agree? Okay, good. So solutions, let's say a general solution, the set of solutions is of the form x and minus x. That's what a general solution looks like. Okay. Now we only want one, right? We're trying to construct a basis of these eigenvectors. Okay. If we take two of these, let's say 1 and negative 1 and 2 and negative 2, they're linearly dependent, right? So we can only gain one eigenvector from this eigenvalue in this case. Okay, so so if we take any non-zero x, for example 1, so 1, negative 1 is an eigenvector corresponding to alpha 1 equals negative 1. Good? Verify that A, our given A, let's write what A was. A is no longer on the board. A was 1, 2, 3, 2 times 1, negative 1. That's AV equals alpha V. Negative 1 times 1, negative 1. Verify this. Good? So we found an eigenvector and an eigenvalue. That was one of them. There's another one. So now there's alpha 2, which was 4. Let's solve the system that results in plugging in a 4 here. Okay, so what do we get? we get the system 1 minus 4, negative 3, 2, 3, 2 minus 4, negative 2, xy equals 0. Right? This is the system that we get for the second eigenvalue in this example. Right? And we want to solve it. Okay. So, again, there's not... It boils down to one equation, right? And the equation is minus 3x plus 2y equals 0, or 3x equals 2y, right? So we get, let's put a line here. So we get 3x equals 2y, or x equals, we can write y equals, right? So y equals 3/2 of x. Do you agree? Okay. So a general solution is what? Of the form x and 3x over 2. That's what a general solution looks like. And therefore, I'm trying to leave this on the board. Therefore, for example, 1 and 3/2 is an eigenvector corresponding to alpha 2, which was 4. Verify that 1, 2, 3, 2 times 1 and 3/2 equals 4 times 1 and 3/2. Good? Okay, so let's take a blue here. And recall what we have. Maybe we should highlight these two statements. Negative 1, 1 is an eigenvector corresponding to the eigenvalue alpha 1 equals 1. Good? And 1 3/2 is an eigenvector corresponding to the other eigenvalue alpha 2 equals 4. Okay? Any questions on the procedure that we did so far, on everything we did so far? Okay? We started with A. This was A. Okay? We discovered that alphas and xy's that give eigenvalues and eigenvectors are going to be solutions to this system here. Therefore, we found first, for which alphas does the system have non-zero solutions? And in order for that to happen, the determinant of the coefficient matrix had to be 0. So we found the determinant of the coefficient matrix. It's a polynomial in alpha. Found the roots. The roots are those alphas that give determinant 0 for this polynomial. Okay? For those alphas, we solved the system. That's how we found xy's that are eigenvectors. Okay, good? Everybody? Okay. So let's say a bit more stuff before we actually move to stating the general theorem. So here's a first remark. This is going to be part of the theorem as well. So the remark is, any two vectors of the form x minus x are linearly dependent. Do you agree? And likewise, any, what was it? It was x and 3x over 2. Right? But, if we take one of these and one of these, non-zero ones, they're going to be linearly independent. That's a theorem. It's easy to check when there are only two of them, because checking that two vectors are linearly independent is just checking that one is not a multiple of the other. But this is going to be a general statement. When you're working with a 4x4 matrix, and you have maybe 4 alphas, and for each one you find the solution, you don't need to check that each one is linearly independent, that the set of the 4 are linearly independent. That's a theorem. Okay? Eigenvectors corresponding to different eigenvalues are always linearly independent. Okay? So that's going to be the theorem. But in this case, 1, -1, and 1, 3/2 are linearly independent. And that's always going to be the case. Okay? Is the remark clear? Okay? Eigenvectors corresponding to different eigenvalues are going to be linearly independent. Good? Okay. So now we're ready to complete our task, right? We want to diagonalize that 2x2 matrix A. Okay? So define, we know what we need to do. We need to take the basis comprised of these two eigenvectors. Define B to be the basis 1, -1, and 1, 3/2. Note that this is not the standard basis. It's a different basis. The standard basis won't do it, won't do the job. It's a special basis. We found it by means of 3 boards of calculations. Usually it takes a lot less time and a lot less space because you don't need to explain everything in the ideas. It's just a kind of a routine calculation. But still, we worked a bit to find B. Okay. So B is a basis for our space, R2. Right? And it's not just any basis. It's a basis comprised of eigenvectors. That's how we got to B, right? Okay, so what does it mean? Therefore, if we take T, let's call this guy, let's give them names. So let's call this guy B1, little b1, and this guy little b2. We didn't call them b's, we called them v's, right? Let's call them v's. This we're going to call little v1, and this one is little v2, right? So T of v1 is precisely alpha 1 v1, right? That's what it means that it's an eigenvector, and we know what this alpha 1 is. Alpha 1 is the alpha 1 we found, corresponding to v1. It was -1, right? And T of v2 equals alpha 2 v2, right? And in our example, let's rewrite it as actual numbers. It's -1 v1 plus 0 v2. And this is 0 v1 plus 4 v2. These were the eigenvalues, right? So the matrix representation of this map T, which was originally given by the matrix A, the matrix representation with respect, not A was its representation with respect to the standard basis, but its matrix representation with respect to the basis B is going to be this diagonal matrix. So the matrix representation of T with respect to this basis of eigenvectors that we constructed, B, is none other than the diagonal matrix -1, 0, 0, 4. That's our D. Good? Everybody? Okay. Here's another remark. Here's another remark. Remark. So we know that the A we started with and the D we derived, the diagonal one, what can we say about them?
Similar.
They're similar, right? They represent the same linear map. A was the one we started with, and D represents T with respect to the basis that we found. So A and D are similar. Similar because by definition they represent the same map, T. But similar matrices, there's this P, this invertible matrix that gives the similarity by D equals P inverse AP, right? And in this case, we even know precisely what P is. Okay, so let me tell you. So, which way I wrote it? D equals P inverse AP. P is given by taking the eigenvectors as columns. By, why given by? P equals, the eigenvectors were what? 1, -1, and 1, 3/2. i.e., the columns of P are the eigenvectors. Vectors. So the diagonal elements of D are the eigenvalues. The columns of P are the eigenvectors. Okay? And this is gonna be a theorem in general, but what I want you to do is to verify it in our example. Verify that D, which was -1, 0, 0, 4, eigenvalues on the diagonal, equals P inverse times A. A was, I forgot what A was, 1, 2, 3, 2, times P, where this is P. Okay? And you need to find what P inverse is. Not a hard task for a 2 by 2 matrix, but do it. Okay? Question? We're good.
How did you position that P?
How do I know that this is true?
The P, that's the P.
I didn't say it. I didn't say it. I just said this is a remark. We're going to prove it. Okay? So what's important is to position the eigenvectors as columns in the same order that you position the corresponding eigenvalues across the diagonal. Okay, so if you took -1 first, you need to take the corresponding eigenvector as the first column. And you took 4 second, you need to take its corresponding eigenvector as the second column. Okay, good? Okay. Good. So this wraps up this example. Okay? And what I want to do in the next lesson is start with a theorem that's going to fill an entire board. But all it's going to say is, hey, this is what we do in general. The eigenvalues are the roots of the polynomial determinant of a minus alpha I. Those are the eigenvalues. The eigenvectors are the non-zero solutions of the kernel of a minus alpha I for each alpha. Okay? Vectors corresponding to different eigenvalues are linearly independent. That's going to be that theorem. It's just going to say everything that we did as a theorem and conclude with the statement that the D we get by putting the alphas along the diagonal is the diagonal form of T with respect to the basis of the eigenvectors. Okay, that's going to be the general theorem. We're going to write the theorem. We're going to prove a bit. Okay, that's going to be a bit, right? You don't like proofs, at least some of you. It's going to be a bit more theoretical. We're going to prove some stuff. And then we're going to do another example. But the next example, on the one hand, it's going to be a 3 by 3 one. So there's going to be a little more action going on. On the other hand, we're not going to pause and do it slowly and explain each line from the previous one. We're just going to do it. Write the determinant of a minus alpha I and find the roots. Boom. Okay, we're just going to do the bottom lines of everything that we did very gradually in this baby example. Okay? Okay, good. Questions? Okay, wonderful.